How can you explain some of the very difficult concepts in physics, mathematics, chemistry, or biology? Well, there's an application called PhET, PhET, interactive simulations. Now, it's an application that I use quite often to explain situations which are difficult to set up, say, in a physical situation in a laboratory, because either the stuff that you want to explain is too small, okay, for students to see. So let me show you what I'm talking about. So for example, let's say that you want to show, say, the bending of light. Okay, you can easily set this up in a lab situation, but it's easier to explain it when you're using this application. So for example, you can choose whether you want a ray or a wave. Okay, I'm gonna opt for a ray, and this is what the ray would look like, and this is what the wave would look like. Okay, so I'm gonna opt for a ray. Now what it's showing is the refraction of light when it passes through a boundary, and the boundary in this case has been created between the air, so air is chosen here, and water, so water is chosen here. Now you can change that to glass, but let's keep it to water for now. Okay, then what this enables you to do is to change the direction, or to change the angle at which this ray is with respect to the dotted line, and the dotted line is called the normal. So the angle between the normal and the ray can be changed. So I've just made it very small, or I can make it bigger and bigger and bigger, and even 90 degrees, which is there. So at 90 degrees the light or the ray will just go along the boundary. So that's the boundary I'm talking about. If you make it bigger, there is some reflection taking place, but there's also refraction taking place. So two phenomena are taking place here. Okay, so let's see what happens when we change the water to air, for example. Okay, if it's all air, then it means there is no refraction or reflection taking place at the boundary, and this is the boundary, by the way. So there's no refraction or reflection taking place. Okay, let's change it to a wave and see. So same thing, no refraction taking place. Okay, the ray is clearer to show. Right, so let's change the air here to, say, glass. So again, there is reflection and refraction taking place depending on the angle between the ray and the normal which is the dotted line. Okay, so let's so I can remove the normal by just clicking on there, or I can add it back. Okay, this one here is showing a prism, and what happens when you change the angle of the prism. So at some point, look at that, that's brilliant. Okay, so these are things that you can easily show by connecting the iPad to an interactive whiteboard. If I've got more than one ray, let's see what happens. Okay, if I've got that, that's actually showing. There we go. There we go. From white light is being split by the gray. Okay. Let's change it to a circle. In fact, we can put two of these together and turn this one around and put it here. Look at that. Brilliant. Let's do this. Make it go straight. It's going straight. Brilliant. So actually, if you put two prisms next to each other, then you can reverse the refraction which has taken place, so that the ray goes back to its original direction. Let's see that. You can do a lot with these. This is something that you might struggle to set up, and you can change the color of the light by just changing the wavelength, which is measured in nanometers. Okay, so from the lowest wavelength to the highest, be from red to blue, and the object is glass. If you change it to water, this is what happens. Let's change it to air. Okay, so if it's air, it's just going to go through like that. Right, so there are more tools here. So let me show you another. Quite like this one, Faraday's law. So Faraday's law will show you what happens when you take a magnet, and the magnet is a north and a south pole, and I think you can, let's show the field lines, right? So if you move the magnet and it cuts the lines, it cuts the coil, and that's the coil. If it cuts the coil, then what it's doing is it is inducing a current in the coil. Okay, and that will create enough current to light the bulb. Okay, so this is called electromagnetic induction. This is what happens in a power station where electricity is generated. We have big giant magnets, as represented by this tiny magnet, and big coils of wire, and there is relative motion between the coils and the wire, which induces a current in the coil, and that's electricity that we use in the homes and in industry. You can see if you move from right to left, it goes in one, the current goes in one direction. Okay, then if you move in the opposite direction, the current also changes direction. Let's put two coils. So you can actually have more than one coil. Okay, so here what I'm doing is just reversing the polarity of the magnet from north to south. Let me put one coil, put it in there. So by just changing the polarity, I can also induce a current. Okay, that's a good one. Let's see. Let me show you one more. I like this one as well. So in this one, it's showing charges and a balloon. So if I rub this balloon onto this piece of clothing, okay, it's going to attract all the negative charges, so that the jacket now has a net positive charge, which means that the balloon has a negative, so it's attracted by, if I just let it go, it's attracted by the jacket. Okay, if I put it close to this wall, then the negative charges are going to repel the negatives on the wall. Okay, this could be anything, it could be a wall. Now the point to note is that the positive charges are not moving because they are inside the nucleus of the atoms of that material, okay, which is why they are in one place. But the electrons are able to move because they are free to move around. That's why they can be transferred from the jacket to the balloon. Okay, so I've removed the charges. This is what we would see in real life. Okay, we would see an attraction like that. Show charge differences and show all charges. So with the charges now we understand why it is attracted to this wall, because the negative charges have been repelled and these positives are attracting the negative charges on the balloon. But because there is less positive charges attracting the balloon to the wall, if I put it there, it's attracted towards the jacket instead of the wall. But if it's closer to the wall, then it can just get stuck to the wall. Okay, so that's a good one. You might like to see this one as well, just before we close this one. So this is showing what happens to the interchange between potential energy and kinetic energy. Okay, so as the man is going up, he's gaining in gravitational potential energy, and then that turns to kinetic as it comes down. So as he's going up, the kinetic energy is being converted to gravitational potential energy. Let me slow it down. So now he's gaining in kinetic and losing in gravitational potential. So there is that interchange. Okay, let's see if we can put a pie chart of the energies. Okay, so the green is the kinetic and the blue is potential. So it's getting kinetic green, and then starts getting the blue, which is potential, until all the potential has been changed to kinetic, and vice versa. Let's show it as a graph and remove the pie chart. So as a graph, you can see as potential comes down, it's converted to kinetic and vice versa, and the total is always the same. So if you, let's pause it, let's play it a bit and then pause it here. So if you add the kinetic and the potential, you get the total. There is no thermal here, it's very small, that's why it's not showing. Thermal would be if some of the energy is converted to heat. Let's use the graph a little bit. This is becoming very interesting. So the speed as well, we can show the speed, we can change the graph, put the man up there, and it's just going to change all the potential into kinetic, and then like that. Let's try this one, and then once it stops, by the way, it's all converted to heat. So let's see, or the potential into kinetic. Then when it stops, okay, that's the total. So let's see if we use this one. You've got potential, kinetic, then goes potential again, then kinetic, then potential again. Okay, that is very exciting. What if there is friction? Okay, what if there is friction? And again, we get our bar chart. So now there's thermal because there's friction. Okay, and eventually the thermal is increasing, and so all the kinetic and potential energies have been converted to thermal. That's very interesting. Okay, so let's try again. Potential and kinetic being turned to thermal because now there's friction, and the thermal is increasing. Potential and kinetic, they are interchanging but getting smaller and smaller until the person comes to stop. There we go. Right, let's try this one. This one says skate park, but it's blank, so we're gonna forget it. Okay, right, so I think that's it. I mean, you've got the physics, but you've also got the biology, and you've got, although that one, balloons are static, is hardly any biology there. Okay, maybe pH scale, color vision, and the neurons. Then you've got chemistry, which is all this. Then you've got the physics. I've shown you a bit of math. Okay, then this is multiplication, but I'm not going to show a lot of it. So multiplying, that's something you can look at if you do get the application. By the way, you can just go on their website as well, PhETcolorado.com. If you go on their website, you can download this for free and just use them, but I think you need to register with them, but you can get them for free. Okay, so there's the maths, there's a bit of earth science. Let's go to university stuff and physics, and that's what you get. Okay, so I think that's it for the PhET Colorado PhET interactive simulations. Very good if you're going to use them in a classroom setting where you cannot always get hold of the equipment, and even if you have the equipment, it's difficult to explain what's happening at the atomic level. Okay, so I'll see you in the next video.